So let's get started. Never mind. So we're going to go into what is Elasticsearch and why do we want it. We're going to talk about the differences between database search and searching with Elasticsearch. We're going to be talking about why we're still not using it on GitLab.com, which we're trying very hard to do, by the way. We really want to use it. We're going to talk about how the initial setup looks like for self-managed users. We're going to talk about the schema and the analyzers that we use, how we interact with Rails models, how the searching actually works, and finally, we're going to talk about GitLab Elasticsearch Indexer, which is a new indexer based on Go that we're using. That will be replacing the Rails-based indexer soon. So first of all, what is Elasticsearch? So it's a search analytics engine built on Apache Lucene, which is a full text search engine. It's open source, it's RESTful, and it's distributed. You can have multiple shards that talk to each other, so you can distribute the data and the work of finding the data. It's actually the most popular search engine for both log analytics and full text search, and with good reason. It is very, very good at what it does. It accepts JSON documents using its API, or it's got ingestion tools such as Logstash. The Logstash actually uses Elasticsearch in order to, so you can feed, Elasticsearch via Logstash. It automatically stores the original document and adds searchable references to that document in the cluster's index. So then it permits you to search and retrieve the document using the Elasticsearch API. And you could also use Kibana to visualize your data and build interactive dashboards using the data. It's very high performance. Thanks to it being distributed, it enables you to process large volumes of data in parallel. And it's near real time. Reading and writing data usually takes less than a second to complete. So, by the way, we do not want to use Elasticsearch for all of our data for the usual reasons. It's not a relational database, so it doesn't hold any relation data between your documents. It's purely document storage. And what I mean by that is that it's closer to, say, a MongoDB than it is to a PostgreSQL, for example. So we talked about what it is. Let's talk about the differences between database search and Elasticsearch. And the main difference and the main reason why we want to implement Elasticsearch on GitLab.com is that it allows for global code and commit search. So right now, if you go to GitLab.com and you try to search for codes or commits, you cannot do this globally. You have to drill down into a particular project before you can search for code. So as you can see in the screenshot on the right, we are searching through any group and any project in the code base. And filtered search, which is when you are actually searching for issues inside of a project or a group, that does not currently use Elasticsearch. What you see on the right is the global search, /search that you get when you type in any words on the top bar on GitLab.com. And why isn't it used on GitLab.com? Well, basically, it's very expensive. Using it for all projects would result in a 66% storage increase. And the analysis is available in that infrastructure issue you see there. Our administration support is lacking, so we're working on it. We need to be able to give our administrators more insight into what's going on with the Elasticsearch cluster, allow them easier indexing, an easier way of knowing if the index is stale, for example. We don't have a good way to do zero downtime deploys right now. At a minimum, it requires a Rails restart if we change any classes. Or if we change the schema itself, the classes need to pick up the change in schema. The problem is equivalent to database migrations, but we actually don't have any new tooling around it. So we are trying to figure out how to decouple the schema from the code itself. But it's a pretty hard thing to do. And we do have good news. An MVC is going live very soon, as we've completed enough work in the Epic to allow us to enable GitLab.com for a subset of groups and projects. So we now have a way to enable Elasticsearch just for a few groups or just for a few projects. So we'll be using that to enable it only for GitLab CE and GitLab EE on GitLab.com itself to test things out. So let's start talking about how to set it up initially. So first things first, you have to install Elasticsearch, right? We have the requirements for each version available in our documentation. Basically, you can install nowadays any Elasticsearch between 5.6 to any 6.x version. We then move on to the initial indexing of context after you've installed it. We currently do it via rake tasks, but soon we will be adding this to the admin console. It'll just be a button that you can say, well, index. But currently we're using GitLab Elastic Index rake task that runs all the indexing operations in the foreground except for repository indexing. Repository indexing is a little bit special, and I'll talk about it a little bit more in the following slides. This is suitable for all but extremely large instances, which must run each indexing operation separately in order to avoid overloading Sidekick. This is because when we start our repository indexing, we actually start enqueuing as many Sidekick operations, as Sidekick workers as we can. And finally, we enable indexing and search via Elasticsearch on the admin console. And this is what you see when you're in the admin settings area. You can enable Elasticsearch indexing and search with Elasticsearch as two separate things. This is so that you can start indexing, but still get results via the database while the indexing is ongoing. Because if you enable search with Elasticsearch enabled and your index is not ready or just not indexed at all, you're not going to get results. As a bare minimum, most of our search results require all of your projects to be indexed. And I'm not talking about the repository, but rather the project metadata itself. Because most of our queries rely on the project data in order to check permissions on Elasticsearch itself before we return any results. And you can set the URL of Elasticsearch, the number of Elasticsearch shards, and Elasticsearch replicas, just the normal things. We also have indexing restrictions in place for Elasticsearch, where you can limit the namespaces and the projects that can be indexed. So if you don't want your entire instance to be indexed in Elasticsearch, you can set restrictions. And then only when you are inside of that group or project will the code base use Elasticsearch for search results. This does mean that you lose global search, of course, because not everything would be indexed. So on global search, we use the database when this is enabled. So let's start going a little bit more into how Elasticsearch works exactly. So for GitLab.com, we set all of our objects to have the same document type and live in the same index. In Elasticsearch, you can have multiple indexes, and each of those indexes would hold one document type. And that is usually the way people use it, right? We would have one document type for issues, one document type for projects, one document type for merge requests, and that would keep everything separate, and it would keep the indexes a little bit smaller. Oops, sorry about that. So keeping all of the document types the same permits us to have parent-child relationships, which is actually extremely important for us because otherwise we cannot use the project data in order to filter, for example, issues or merge request searches. It requires us to implement our own separate type checks though, because everything in GitLab codebase is in doc. Like that's the document type we selected, just doc. So we have a separate field in all of our documents that has a type name, and that's where we keep whether it's an issue, whether it's merge request, etc. Now, that does mean that all of our types share all the fields. So we have a lot of sparse fields, which means we could have a lot of wasted storage. But thankfully, since Elasticsearch 6.0, there has been great storage improvements for sparse fields. So we do not get a big storage penalty. It's actually negligible. We should probably move to one index per type. But like I said, we lose the ability to filter by project attributes. Or alternatively, we are forced to denormalize project data into every data class type. So we would balloon storage usage because then we have to copy the same project information that we require. For example, access levels for issues or access levels for merge requests, or whether or not you have permissions to see a project. We would have to put that into every single document type. So analyzers are where the search magic actually happens. An analyzer prepares the data for better searching, and each analyzer increases its storage needs because what an analyzer does is, the way we're doing it is, every analyzer has an option to keep the original data, and we do want to keep the original data, so we have that on. And then each analyzer molds the data into a different format, basically. And they're composed of tokenizers and filters. For example, an analyzer that's used very often is just a plain English analyzer that would turn the string a brown fox into 3 different strings. So there would be a string a string brown, and a string fox. And then we have what are called n-gram analyzers, which would basically turn the word fox, for example, into 3 letters, F, O, X, but also would turn the, sorry, we also have what's called edge engrams, and an edge engram actually would turn fox into F, FO, and FOX. And that's so that we can actually match when somebody searches for partial words, because Elasticsearch will not match a partial term unless you already have tokens that have that partial term inside of them. For models, we use the standard tokenizer, which is what I was talking about, and we have 3 filters. We have a standard filter, which actually doesn't do much. It's just there for Elasticsearch in case in the future they have to add, and it's just an easy way for them to add an extra filter if they need it, which actually on Elasticsearch 7.0, the standard filter is getting removed. So I guess they never needed it and they noticed that they can just remove it. We have a lowercase filter, which normalizes text to lowercase. And also when we're searching, we normalize text to lowercase. So this means that it's a lot easier to match search terms as everything is normalized to lowercase. We're not case sensitive in searching. And we have a custom stemmer filter that we called My Stemmer, just because it's the only one we have, that uses the light English stemmer. And that's the one that knows how to separate English words, for example. It knows that an apostrophe should be part of the word. Then models also have my n-gram analyzer. Oh, again, it's the only n-gram analyzer we needed, so we never gave it a proper name. And it creates 2 or 3 grams for projects, for the project's name with namespace itself. And 2 or 3 grams it means that you're just getting partial strings of 2 or 3 characters. We also have way more interesting analyzers for repositories and commits. We do a ton of tokenizing with ASCII folding and lowercase filters. ASCII folding basically turns every UTF-8 character that could be ASCII into ASCII, and lowercase just makes everything lowercase. We do have a special filter called the code analyzer. It uses an edge engram filter that creates grams between 2 and 40 characters wide, and that is also, so we use this for code, and basically means that if you have a very long string with a lot of periods, like if you call a very long function and then you add a parentheses and you add some arguments, sometimes you want to just find everything that has the very long function name, just the function name. So if we did not have this edge engram filter, we would actually not be able to find that function name. Or if you want the partial function name, like functions that have a specific word inside of them, we need this in order for Elasticsearch to be able to find it. We also have a custom code filter with a ton of reject patterns. So we are basically separating camel case function names so that you can find different words inside of a camel case function. We also extract all the digits. We also extract terms inside of quotes. We separate the terms on periods, and we separate path terms, terms between slashes. And this is again because if we don't do that, then you cannot search for just that term that's inside of periods, for example. You would have to search for the entire string until there is a white space. We also have a custom SHA analyzer, which tokenizes using an engram between 5 and 40 characters, and that directly maps to how Git uses SHAs to to identify a specific commit. So if you put a commit SHA into the search bar, we use this analyzer to turn like a 40 long SHA into 19 long, 18 long, 17 long, 16 long, all the way down to 5 long. And that's how we can allow you to search for the specific SHA, no matter how many bits you're giving us. So how do we interact with Rails models? Well, we use a customized Elasticsearch Rails gem to link up our models with Elasticsearch. We needed to customize it a bit because our way of doing the document type is not normal. We have a single document type for all of our models, and that's not something people usually do. So we had to customize it a little bit, and you can find those customizations under a, oops, sorry, I wanted to get out here. Under a gem extensions folder, you'll be able to see all of the different changes we made to the actual Elasticsearch model adapter to be able to actually support this change. So we have an application search module, which is the entry point that defines callbacks and shared methods for everything except for repositories. After that, each class defines their own search module. So we have project search, issue search, merge request search, and node search, for example. And these classes define the basic Elasticsearch query structure and any special indexing concerns. So application search defines, for example, the basic project filter. We define the basic project filter right here. You can see that we are defining all of our settings, such as the number of shards, the filter that I was talking about, the light English stemmer, a tokenizer for the project path. And we go down. These are all of the fields that we have available to us. This join field here is actually how we do parent-child relationships. So the project can be a parent, and then issue, merge request, milestone, node, blob, wiki blob, and commit can be child of the project. And we need this. Sorry, we do have a ton of fields since everything is in the same index. I'll talk about the after commits in a few seconds. But what I really want to show you here is the basic query catch. Here we go. So this is the absolute simplest hash we ever sent to Elasticsearch. We have a query of Boolean type that must match certain fields with the query, and we use the AND operator. So the more terms you give us, they all have to match. And we have a project ID filter where the parent type has to be project and the query has to match the project ID query, which is right here. So you can see that if we check if the user can read cross project, which basically means the user is an admin, then we send an empty project ID. We want them to be able to read everything. Otherwise, we pick project by memberships. We pick projects by visibility because if the user is not a member of it, the project has to be public. Otherwise, if the project is internal, then we need the user to be a member of it. So we have projects by membership as well. We also have projects by feature. So we can, if we are going to limit by members only, then we need to make sure that the feature is enabled and the user is a member. Otherwise, we just need the feature to be enabled for public projects. And this is actually used heavily in issues, merge requests, etc., to make sure that we are only returning issue results, for example, for projects that actually have issues enabled. We also have Elasticsearch Git repository. That's the one that defines how blobs, wiki blobs, and commits interact with Elasticsearch. We need a separate module because they're completely different. Repos are not on the database, they're actually on disk. So we need to talk to Gitly in order to get the actual blobs and the actual commits. We only index the default branch, otherwise costs would skyrocket. The only branch we ever index is master or whatever other default you have set. And we currently have two indexers. We have a Rails script that's actually very slow and is due to be removed soon. And we have GitLab Elasticsearch Indexer, which is written in Go, and knows how to talk to Gitly, knows how to talk to Rails, and it's a lot faster. It greatly improves speed by almost 10 times for certain scenarios, and lowers the resource usage. And it's just because Go is better at memory handling. Though this is still memory hungry, we're still loading all of the blobs into memory when we are indexing. But we do improve our I/O a lot, which is usually the bottleneck when we do repository data. And we improve encoding detection because we're using actual C compiled modules in this case. And it also allows us to hide from the Sidekick out-of-memory killer. So before we have problems with our Rails script because it gets queued from Sidekick. So since it gets queued from Sidekick, it gets pulled from Sidekick, it shows up as, and it's in Rails, it's a Ruby script, it shows up as part of how much memory that worker is using. And so Sidekick actually has a limit of how much memory we can use, and we start getting killed by the out-of-memory killer. So by pushing this off to another process entirely, we can hide from that, and so we can use as much memory as we actually need to. Now, it's only used for blobs, which includes wiki blobs and commits. Now, wiki blobs is actually a new thing because we found out last milestone that we basically had a broken indexer for anybody that was no longer using NFS. Anybody that migrated over to Gitly, because wiki blobs are blobs. They are on this, and they're not on the database. So we actually have to treat them exactly the same as other blobs. By the way, whenever I say blobs, I do mean files. So all of the code files in a repository or any other file you have in a repository. And it's a good idea to note right now that we do not index binary blobs. We only index things that can be detected as text. So any images, of course, get ignored. Any binaries, as in executable files, those get ignored. We also do not index very large files. Do not quite remember what the limit is right now, but it is in the code base somewhere.
5 megabytes, I think. I could be wrong.
How much, sorry, Nick?
I think 5 megabytes, but I could be wrong.
Right, and 5 megabytes is actually very, very large text files. So it's a very, reasonable limit. So it talks to Italy, and it gets a diff between the last commit as found in index status and the current SHA. Now, index status, we keep index status in the Rails database. And it really is just there to know what is the last commit that was indexed for that particular project. Because we don't want to re-index everything every time. We have some gigantic projects on GitLab.com. And so we need to keep track of what's the last commit that we've already indexed, and only index all of the new files that have come in after that. And by new files, I also mean updated files. So we can catch all of the updates that have happened between the last commit and the current head or the current SHA that can get pushed to us. And any deletions as well happen at this point. And the only problem here is that we are assuming that only commits are ever added. That commits are only ever added, that they're not removed. So, you know, like when you do a force push, for example, you're changing history. Some commits have gotten removed at that point. So there's an issue right there where you can read more about how we're going to try to fix that. But going back to application search, that one defines callbacks, right, for incremental indexing when a model gets updated. So we have insert, update, and destroy triggering Elasticsearch updates via the Elasticsearch indexer worker. Oops, sorry. I keep forgetting how to use Google Slides. So as we had seen a few seconds before, we have an after commit on create, on update, and on destroy. And this actually gets included in all of our project search, for example, include application search, and project search gets included into projects. So we have that available there. Same with issues, MRs, etc. And we have the Elastic indexer worker performing a index, update, or delete, depending on what we're doing. We always need to know what the parent is for a particular class, because Elasticsearch requires us to route all of the objects that have a parent into the same shard. Like Elasticsearch has multiple shards. That's how it does its distributed model. And so all of the children of a particular parent, in this case a project, need to live in the same shard as the parent, which does mean that we can get a very unbalanced storage usage, where if you have a project with 10,000 issues, then that shard is going to be full of issues, or it can be full of files. And Elasticsearch indexer worker really is just enqueuing an index record service or deleting the file directly. And this really, again, just sends a direct operation to Elasticsearch, whether it is index or update. And it can detect if this is the first time we've ever indexed a project. So if this is the first time we've ever indexed a project, there are some extra things we need to do. Usually this would just, for example, get an issue, and it would update the issue description, the issue title, etc. Or if it gets a project that it's already indexed before, so it gets an update operation, then again, it just makes sure that all of your project features are updated, and make sure the metadata for that project is updated. But if this is the first time we've ever seen this project, and the way we detect that is by whether or not you're setting as an index or an update operation, then we have to do an initial index, where we have to grab every single index data association, which is the issues, the merge requests, etc., and we're going to import them into Elasticsearch. If we don't import them into Elasticsearch, then they're never going to be imported in, basically. It's the initial import when, for example, import a project into GitLab itself. Then we would grab all of the new issues or all the new MRs coming in. Otherwise, you have an empty project, you don't really have anything to index. And the repositories actually get updated via git push worker hooks. So we have a git push service, right? And the only thing that does is if we are in a default branch and the project is enabled for Elasticsearch, remember we can filter which project or which group gets indexed. Yeah, and we actually have a Redis lock here because we were having some trouble if we had somebody create a new project as the indexing was going on. So if we should index a commit, we just use Elastic Commit Indexer Worker. And Elastic Commit Indexer Worker is the simplest of our workers. It just calls GitLab Elasticsearch Indexer. And this one, the only thing it has to know is whether we're going to use the new experimental indexer or not. The way it chooses whether to use the experimental indexer or not is by checking the application settings. If we have the setting to use the experimental indexer enabled, and if the binary exists in your path, the binary must exist in your path for you to be able to enable that feature, then it'll use the new indexer. We should really rename this, by the way, because it's not experimental anymore. It's basically a beta to be a full release. But you know, we changed the documents, but nobody looks at this, hopefully. But anyhow, we set up some environment variables. You know, we set from what SHA to what SHA we want to index. And the only thing we do here is update the index status and run the indexer. So running the indexer really is just calling the indexer. If you don't have the experimental indexer enabled, it'll go to the Ruby script. If you do, then it'll call the binary for the Go code base one. And we have a few extra bits for knowing whether it is a wiki or not, because if it is a wiki, we have to send the wiki repository, not the project repository. And that's really it. We just have some extra things to get the index status and what attributes we have to update, because now that the wiki also goes through the Go indexer and we want to do incremental wiki updates, we need to actually send wiki commit and wiki index stat information as well. So yeah, the last commit that was indexed is kept on the database in the index status model. So how does search work? An Elasticsearch query is a JSON structure, and it can contain multiple filters. So we see an example of it on the right side. We can say, hey, this is a Boolean query that must contain the term kimchi under the user attribute. And let's filter out anything that has the value tech under the tag attribute, and it must not contain between 10 and 20 on the age attribute. And then we can also say it should. Now, must and should exist like that because Elasticsearch also ranks your results as to how close they match your query. So depending on whether you must or should, must is a filter, like it must match this, but should just gives it the same must match, but it gives it a lower score. So they would show up later in the results. We implement permissions as Boolean filters, and we can filter for a project that a user has access or for projects with features enabled. So we want to filter, for example, for a public issue tracker, we can do that. And highlighting is given to us by Elasticsearch. If you click there, you'll be able to see the Elasticsearch documentation on how highlighting works. You just send in a highlight field in the query with the field to highlight, and Elasticsearch will tell you where exactly in that field it matched the query you gave it. So the response comes back with a highlight element for each search hit. And it has the actual fragment of the document where it matched. So if you query for fox and you get a quick brown fox something, it'll give you a fragment that says quick fox, and it'll have the match right there where you should be highlighting. We expose Elasticsearch simple query string. We do this because it is a little bit simpler for us, but it also allows the user to use exclusion operators. So you can do a little bit more interesting things than our normal database search. We can do exact search matches, and it is complex, but it is a very powerful way to query. If you click simple query string, you'll be taken to GitLab's advanced search syntax, which is a superset of Elasticsearch and a few filters that we added. So the filters that we added are defined using a GitLab search query, and it allows us to filter by path, file name, or extension. And the way they are implemented is extremely simple. Again, we have, it's in the repository, I believe. Yep. So you just have this search query class, then you add filters. So file name is the file name filter. Then path allows you to filter by path, and extension allows you to filter by extension. And this is just how to parse whether the input matches or not. And if you go into the query class, you'll see how exactly these filters happen. But it really is just adding more terms to the actual Elasticsearch query. And this is what I have. So let's open up the floor for questions in case anybody has any. Let me go ahead and open the document. Sorry for the delay.
Can you link the doc? I didn't actually see in the calendar invite.
Oh, sure thing. Sorry, the document was created right now during the talk. It's in the chat.
Oh, yeah, and I think I joined after you in the chat, so there we go. Thanks, Nick.
Yeah, sorry about that. Having a little bit of trouble opening the doc. Let's close this.
I just piggybacked on top of the prep doc, so it's all in one place.
Yeah, sorry about that. I completely forgot to create a doc. So Kai asks, when restricting by group or project, it sounds like global search is disabled. What does that mean for the GitLab org on .com when this is enabled? Can you demo it in staging? So I see Nick has already been answering a few of these. So thank you so much, Nick. You want to take this one?
I think I'm good on this one unless other people want to go through it. I think Nick and I hashed it out through the.
If one person asks it, then other people are going to be curious as well. So it's good to go through them. In this case, it's just asking, I guess, about there's limited projects that we saw right at the start in the admin settings. You can say only index the GitLab org group, which we're going to do on GitLab.com because we can afford to just index the GitLab org group. It's about 3.5 gigabytes just for that one group, so it's not too expensive. If you have just a group or just a project indexed and set up in the Elasticsearch settings, then if you're on the search page for that group or for that project, you get all the extra Elasticsearch magic. If you're in any other group or any other project or a global level, then you just get the regular ordinary database search with none of the extra features. But that search does still work, which is the important thing. It doesn't disable global search for everybody, which I think is what Kai was perhaps most worried about.
Is the UI in any way different when we talk Elasticsearch and database search?
The only difference in the UI is in the search box, once the results are displayed, there's like a note underneath that just says you're using advanced global search, I think, or advanced search, whatever we call it. So that's the indication is there to the user that they're using Elasticsearch.
Yeah, because I was wondering like how you can use these advanced features if the UI is the same. Like, how would you know that a project is on Elasticsearch or is on database search at the moment when you?
Fair question. So basically, right now, the only way to know is whether or not you have the words advanced search syntax is enabled. I have a an example right over here. You see it says advanced search functionality is enabled right below the search query. That's how you know whether Elasticsearch is enabled or not. And that's fair. We should probably give it a badge or something. We're actually thinking about a few different ways to surface whether Elasticsearch is working or not.
The list of tabs differs as well, but that's very subtle.
Right, yeah, like we have the code and the commit tab will not show up if Elasticsearch is disabled for global search. So if you have the indexing this enabled only for a few groups or a few projects, then sure, for the group, you'll see code and commit, and that'll be different. But for the project, it'll look exactly the same. So sorry, let's go ahead and switch over to Cody then. He says, we kick off as many Sidekick jobs as we can. So Elasticsearch Indexing has taken down GitLab before on self-managed. So is there a way to be nicer? So we're actually enqueuing even more jobs nowadays, I believe, than we used to. Because yeah, we used to just do a batching of a couple of thousand projects and then keep going from there. But I'm pretty sure that the way to fix this is not really us being nicer, but rather the Sidekick configuration itself. You know, make sure that you have that Sidekick queue in a cluster that will set up in a way that will not take over the cluster. Basically, you know, set it in a lower priority cluster.
Okay.
And confirm for me.
Quick question about that. You might not be the right person to ask, but maybe you can point me in the right direction. Are we configuring Sidekick that way by default right now, or is that something that we're going to have to keep in mind with all of our self-managed customers going forward?
We have all of these queues. I don't remember where they're.
Because I don't think we do clustering by default in self-managed for Sidekick.
Right. We do have all of these queues separate, so they can be set up like that. And I think the way that the configuration is done is via Chef, not via GitLab itself. So yeah, this is going to have to be more of a how the initial configuration is happening.
Okay. Cool. Thank you.
And for your next question, Cody, are we close to the beta indexer being stable? Yes. We are actually going to get rid of the Rails indexer very soon, and we're going to start using the Go indexer as our default indexer as soon as next month.
Okay. Awesome.
And we actually are not fixing issues in the old one. So right now, wikis, for example, are broken on the old one for wiki indexing. If you don't have NFS anymore, like a lot of our users are moving on to Gitly. If you're using Gitly and you're not using the Go indexer, you're going to have a bad time.
Okay, good to know. Thank you.
So Ethan then asks, do permission checks rely on existing permission models in the Ruby code, or are they redefined to enforce an Elastic? And I see Nick already answered that one as well. Thank you so much, Nick. You want to take this one then?
Yes, I think you showed off some of those permission filters in the code earlier. There is a huge amount of duplication here, and to a great extent it's necessary. Just for a start, to support pagination of all things. If Elasticsearch doesn't know which issues, etc., the user can and cannot see, then it can't give you the correct results and you can't paginate them properly. So yeah, we duplicate all that logic again in Elasticsearch. There's a lot of it. It's very sensitive, and there have been bugs in it before. I don't know of any bugs that expose data right now. If you find one, then it's probably going to have to be P1, since we're going to start turning this on GitLab.com at some point. So feel free to look for them. I would love to find them if they do exist.
So I do have the relevant methods here on screen right now. We have to re-implement all of this because we have to send it all as a JSON document in order to be able to query against it. And we query against it instead of filtering in memory, because it would be extremely prohibitive to do this in memory. I mean, we're talking about sometimes we return thousands of results, and if we're going to paginate this, we got to paginate enough to get like the first 20, and then we got paginate enough to get the second 20, and then how do you keep all of those pagination things in sync? Because every single time you go to the next page, you lose all of your state. You don't have any state in a RESTful environment.
And one thing probably worth calling out there explicitly is if you're not an administrator, but you are a member of, I don't know, 20,000 projects, every Elasticsearch query you do will send those 20,000 project IDs to the Elasticsearch cluster. Such is life. It's horrible, but it does work. I think we only send the project IDs for private and internal projects, and that's how we keep it managed.
Yeah, we don't do a huge amount ever. Otherwise, we would bring down the cluster, I think.
So on the somewhat related to the permissions, but also to like re-indexing stuff, because when you change stuff on the site.
Gabriel, we lost you there. Sorry, Alexandru.
Yeah, I'm sorry, my internet might not be great. I'm not sure if you can hear me still. Okay, so when you like change permissions, it will have to be like re-indexed on or updated on the Elasticsearch side, right?
Right. So every time you change.
How do you? No, the question is how do you ensure that like the indexing did not fail? I don't know. Something did not break, and the actual permission update, which sounds like more sensitive, did actually get into Elasticsearch. Is there some sort of a check? I don't know.
So right now we don't actually have any alerts when indexing fails, but I mean we do need to figure out how to make this easier for infrastructure to be able to tell when something's going wrong. Every single time you edit your project, we do trigger indexing updates through an after commit callback. But yeah, if that fails, then you could have a leak.
We rely on Sidekick not losing jobs, and Geo has the same problem at times. You know, there are times when Sidekick does lose jobs. We retry the jobs a couple of times. If that fails, we go into the dead job queue, and from there, we only keep the last 10,000 of those. And if the index gets badly out of sync, your only real option is to re-index from scratch, which is part of why making re-indexing easy is so important.
Right. And that's also why we've switched so many things to using Sidekick directly. It's a lot easier to have Sidekick retry, and we can rely on the Sidekick's at least once philosophy. Sorry, so the next question is Blair. Can we leverage built-in filters and tokenizers from Elasticsearch to allow language-specific analyzers for the code search? Right, the current analyzer does not cover their code language. So that's a very, very hard problem because every single time we add another filter, we're adding more storage as well. So you're talking about, you know, either adding something that will detect what language each thing is in before sending it to Elasticsearch, which I do not know if it's possible because we then have Elasticsearch analyzers that run on the Elasticsearch cluster itself with no way of really hinting to Elasticsearch, hey, don't use that analyzer, use this one instead for this particular document. So in order to implement this, we would actually have to add a bunch of analyzers for the blob content, which means you know, basically one copy of the document per language.
I just didn't know if are there any like case studies, like, because I would imagine that Elasticsearch is being used to index, you know, code and search for code other places. Maybe that's not true, but I wonder if there is, like, this is just me kind of like spitballing, like, is there some like resource out there that we may be able to tap into?
I'll just say from a product perspective, and I think I got tagged on that issue the other day. I think the concern is super valid, and I think it's something that we need to look into. And the impacts on like index size and what all we have to do and adding more filters spawned a bunch of other discussion. And it's one of those things that I think we just got to keep testing and iterating on to get broader coverage. I think it makes sense to strive for broader coverage on different languages, especially in some of those use cases where the search just flat out can't return it because we've already decided it's some other language than it is. So I think it's something that we should just, we're gonna have to keep top of mind and keep working towards.
Right. Sorry, Blair, I promise you that we are looking into it, but it's just, we have so much problems with how much storage it takes that we got to be careful with what we add.
I understand. Like because I've dealt with customers that are like, oh, why is it like this much storage? And we're like, oh, that's Elasticsearch. So I totally get it. I just wanted to bring it up.
Cool. And Nick wanted to let us know that the blob limit is actually 1 megabyte, not 5, and it is not configurable. So Cody has an issue for allowing configurable max blob size. So that'd be nice for self-hosted people.
That there is one thing to consider when considering Elasticsearch is that whatever you change in the document usually requires a full resync of the whole thing, right?
Whenever we change our schema, then that requires a full reindex. Yeah, and that's because Elasticsearch doesn't really have a good way to transform data, and we would have to go into the database anyways to know how to transform it. So we usually have not. We don't force reindex normally. It's just, for example, this year we went from Elasticsearch 5.5 to supporting 5.66. And that required a complete re-engineering of how we do our relationships. Before, we were able to do a very different sort of relationship in Elasticsearch, but they got rid of that, and now we use parent-child relationships. So that made us change our entire schema. And so that one was a huge change. It meant that nothing would work if you tried to use the old index that you had. So, and we do try to batch up whenever we make a schema change. So we had a few small ones, like there was a typo in one attribute, and we were not actually indexing the internal ID for one of our objects, but they were very mild, only used for display things. So, we didn't really say, hey, you need to reindex. We just waited until everything was ready, batched them up, sent them out. And that's when we said, hey, you got to reindex. So Stan wants to know where parent-child relationships come into play. Stan, you want to take over?
Yeah, you stopped sharing your screen. I find it hard to sometimes how to visualize our data without using Kibana, and I don't know how many people actually use it, but I will share what I have a simple Kibana instance that has indexed some data. So I think to your point earlier about like everything's in one type, I think this is what it's showing, right? Every field
so
that
everything
possible.
is of the doc type. Yeah.
So I find this very illuminating because sometimes it's hard to understand what you're saying without actually seeing this kind of thing.
But you're actually filtering by block content, so that's not really something you want.
Okay, but like for example, I can filter every project, right? That's the type.
Okay, cool.
So
right.
This will give me a set of projects in the database. So you mentioned parent-child a lot. I guess I'm just wondering where we might see this in Kibana.
Right. The join field right there. You have right below issue access level. That join field is so when this is a parent object, so it doesn't really have any interesting data. It's just a project. But if you go to an issue, for example, you'll see.
Any on it, but okay, that's good to know though. So that's useful. And I'm curious about like Boolean filters, and because Kibana allows you to do all sorts of cool searches, are we thinking about exposing some of those kind of things as well?
So we currently only allow you to do the simple query string, and I think it does some Boolean searches. Let me look up the Elasticsearch.
It basically supports everything Google search does. So you can do -foo to say not foo, for instance, that kind of thing.
Right. So we have a plus for an AND operation. We have a pipe for an OR operation. And minus is negating a single token. If you do quotes, then you're saying, hey, this is a phrase. I want the whole phrase to be together. And you
It has
have
field searches as well, but we don't make much use of those.
yeah, you can have edit distance as well. So you can do some interesting things if we were actually adding language analyzers. Sorry, I'll go ahead and search my screen again as soon as I can find the Zoom window. Sorry about that. Share desktop 2. So Greg wants to know, what are we going to do about ElasticSearch Go indexer needing 1.11 or newer, but most Linux distributions don't have that in their default repos. So Nick, do you want to take that one?
Yeah, it's a dependency. It's not a unique dependency to the indexer. Sorry, I've got Lord of the Rings going on in the background. If they don't have it, they'll have to install it if they're installing from source. As I think it was DJ said, we've already installing it by default in Omnibus. And that's the path that we really want to make easy for people. If they're running, I don't know, Debian stretch, and they need Go 1.11, they'll just have to install it as well.
Right, and we are including it in Omnibus, right?
Yeah, absolutely.
So yeah, the indexer does come in Omnibus, so that's already a file binary. So they might not need Go at all.
They don't. If they're using Omnibus, they don't need a separate Golang install.
I think it's more of a documentation issue because if you go to the Elasticsearch integration official docs, which I linked, there is no mention of it being installed in Omnibus, and it does directly instruct the user to git clone, make, and make install, which if they do not have that dependency installed, it will fail. And it's not just for Debian Stretch, it's for CentOS 6, CentOS 7, Ubuntu 16.04, and I believe a default Ubuntu 18.04 would also lack that. So basically, last week I was trying to follow the documentation to set it up, and as is, if you follow that documentation on most Linux distributions, you will fail at the make step, and there is nothing that says it's included.
Yeah, so we need to change this to include that we do have it already included in Omnibus, and also letting them know that they need to install Go from source if they can't find it in their official repo.
Yeah, we can. Can you create an issue for that, Greg?
On it.
Thanks, Greg.
Thank you.
See, Matt, we only index the master branch. You know, we could do some sort of interesting stuff with only indexing things that have changed between master and another branch, but then it would be a lot of trouble keeping it updated. Plus, what we want to do with Elasticsearch is allow you to do global code searches, and global code searches really only matter on the default branch, so master usually.
Although
it would
GitHub
be,
has the same restriction as well, don't they?
yeah, it would be cool, but
oh, it absolutely makes sense to limit it to master. I was hoping that was your answer.
Yeah, we only limit it to master, and we especially want to limit it to master because of our storage requirements.
Yeah, absolutely. Thanks.
Cool to find a way to lower the storage, but you know. Sorry, DJ, what do you mean by tag code search?
Oftentimes, I might know a function name or something that existed in one version of a product, and I want to know what file it was in, basically.
Okay, fair enough. Yeah,
I find this often on GitHub as well when we're using a dependency that maybe is a little old, and I want to see where the thing that's breaking was implemented in the version that we're using, and doesn't really work well.
Yeah, that's fair enough. I mean, you can if you're in the same file, you can just use our history viewer. But if there was a refactor at an endpoint that came from another file, then yeah, you lose visibility if you use our history viewer. So
yeah. Currently, you basically have to check out it locally, and then check out the tag you want, and then search locally in your IDE to find it.
Yeah, could you open an issue for that, please? I mean, it's good for us to keep in mind for the future as well.
Sure.
And when we say a master branch, are we talking about like literally a branch named master, or is it possible to specify some other specific single target?
We're talking about the specified default branch. So if you go to your project, then you see default branch. That one defaults to the name master. So, but you can change that, and we would honor that.
Makes sense. Thanks.
And Matt wants to know how long we retain data in the Elasticsearch indexer. That's as long as the document itself still exists in the repository, it will be there. As long as the issues themselves exist in the database, they will be there. Even if you close them, they still exist. They just have the tag closed on them. So the only way that we remove Elasticsearch index data is if something gets properly deleted. And Matt again, because we must allocate a whole project to a single Elasticsearch shard, do we anticipate needing to manage the uneven growth of shards across a pool of ES nodes? So Gitly nodes storage have uneven growth for the same reason. To be honest, I'm not sure. Nick has some thoughts about that, but it'll be more of our infrastructure team will know more as well. Nick, you want to jump in? He might have left already. It was late of the day for him. I'm sorry. I'm gonna have to ask you to follow up with either Nick or our infrastructure team that has been dealing with the new staging stuff.
I'm on the infrastructure team. That's why I'm asking.
Oh, I'm sorry, Matt. Yeah, you're our first line of defense here. I mean, it is hard. It is very hard because we need, if we want to keep parent-child relationships, we need to keep them in the same shard. It's an Elasticsearch requirement.
Yeah, your rationale makes perfect sense. I'm just wondering about the scaling. You're right. It's a hard problem to solve. Not having an answer right now is okay.
Yeah, I mean that's why we're talking about getting rid of parent-child relationships and having one index per object. But the problem with that is we need to denormalize, which means more storage, and we really don't want more storage requirements. So Lewis wants to go back to Cody's first question. And self-managed clients, if they have a large instance, they need a Sidekick cluster for implementing Elasticsearch. A small instance doesn't really need it, as well. It'll be super quick. We do need at least a few Sidekick workers to be able to keep everything updated, but that's a requirement for all of the GitLab application, right? And I'm not sure who it is that's writing right now. Oh, Cody. Thanks, Cody. Yeah, so it depends on whether the customer notices that things are slow when something is getting indexed. If things are slow, then they're going to need a Sidekick cluster. And feel free to jump in if you feel like I'm not answering the question completely. So Matt wants to know,
sorry, I'll interrupt for just a second. Sorry to stop you there. Nope. I think we can just take this async and research it some more. I'm just throwing this out there for the other people who are curious about it. I think we need to dive in a little bit further and just figure out how to determine whether Sidekick queue is causing pain for other sorts of async actions. So I just wanted to mention that real quick.
Sure thing. So let's get those last two questions out of the way. It's 11:04. I know people have to go back to work. So Matt wants to know, considering the upgrade path for Elasticsearch, would we expect that we need to re-index all data in the future? And that's a yes. And that's why we are trying so hard to decouple Elasticsearch schema from the code base as well. We want zero downtime indexing. We might have to do one maintenance downtime in order to update to that in the future. Hopefully Hopefully we don't. Hopefully it's all a matter of just disabling indexing and then just doing our thing, and the rolling update being enough. But we currently do not have zero downtime indexing. Like we require reload of the classes in order to pick up the new changes. And you said we showed some clever use of n-grams to handle both partial search terms and reduce the need for language-specific listers. So yeah, so that question, it's the same as above. Are we going to add more stemmers for other natural languages? And the question is most likely not, sadly, because of the problem of storage. Every single thing you add requires more storage. We're copying the data. And tokenizing specific programming languages would be interesting. We're trying to keep everything general, and that's why we have all of those. Let me see if I can find them real quick. Where are they? Here. This is why we have all of these patterns. So we're trying to separate camel case things, separate digits, separate things in parentheses, separate terms inside quotes, separate terms in periods, and path terms. That tends to work well for most of the cases. There are some edge cases, of course. I think if you go for Objective-C, for example, you got those square brackets you got to deal with. So that would be something we are not really capturing well with these different rejexes. And I think we're going to have to, deal with that on a case-by-case basis.
Makes sense. Thank you very much.
So we are 6 minutes over. So sadly, I'm going to go ahead and stop it here. Thanks you, everybody, for being here today. And any more questions, please feel free to drop them in the document. I will be checking it later. And I hope this was worth the time for you. Have a great day.